Welcome back to the third talk of our data track today. After a very practical talk, I'm excited that we have some interesting in theory to talk to. Today we're going to listen to Service Level Objective Theory by Emily Gorcenski, Head of Data at ThoughtWorks. Emily, nice to meet you, and I'm looking forward to learn a lot more today.
Thank you so much. So we'll get right into it. Just give me a moment to share my screen. And we should be away. So thank you all for joining me today. I want to talk to you about designing great data products using SLO theory. SLO theory is something that comes from site reliability engineering theory from the sort of distributed systems world. Some of you might have read Google's SRE book that was published for free a few years ago. And a lot of the concepts that I'll be talking today are borrowed from that book and that community. Before I jump into the talk, I'll introduce myself. My name is Emily Gorcenski. I am the head of data at ThoughtWorks Germany, and I'm a principal data scientist with ThoughtWorks. My background is actually in computational mathematics and research engineering, although in the past couple of years, I've sort of fashioned myself as a data engineer as well. And now I'm responsible for a lot of the work that we're doing in data, everything from analytics to machine learning to data engineering and platform development at ThoughtWorks. And yeah, I'm pleased to talk to you about how sort of a bit of our perspective on how we build data platforms and data products. A little bit about ThoughtWorks is not a sales presentation, but I will introduce my company briefly. We're a global software consultancy. A lot of the work that we do is trying to change the way that people think about software and how people build it. We are now spread across the globe in 17 different countries, and we've been doing software development and transformative work for almost 3 decades now. So this talk will be a little bit difficult because in order to get to the concepts that I really want to talk about, I have to introduce 3 different ideas. So in the description, I use the term data mesh. Maybe you've heard it. It's sort of a trending topic in the data landscape now. Data mesh was a term coined by my colleague Shamak Tigani here at ThoughtWorks. So I'll talk briefly about what a data mesh is. The term data product is maybe not so unfamiliar, but here it has a specific meaning. So I will be introducing what data products are. And then finally, I'll also be talking about SLOs and what is a service level objective, how is it different from a service level agreement, and how do we use them. So before I get into the theory, let me just set a little bit of a backstory. The data mesh concept can best be described as microservices, but for data architecture. And what we have observed through our work with our clients, through working with businesses of all sizes, everything from 100-person startups to 100,000-person enterprise organizations, is that we see the same patterns, the same challenges with data. And the hypothesis that we are using with the data mesh concept is that these problems stem not from the technologies, not from the skills of the people, but rather the overall architectural paradigm. And even as we have moved from the data warehouse era to the data lake era, and from the data lake era to the cloud native era, building streaming architectures, things like your Lambda and your Kappa architectures, to your cloud native integrations, it's not changing the way that we see data. It's changing the tools that we use. It's changing the technology that we adopt, but it's not changing this sort of left to right thinking. And in all of these data architectures we draw the diagrams the same, every single time. We start with sources on the left and we have consumers on the right, and somewhere in the middle is some big monolithic object, some data warehouse or some data lake or whatever it might be, some combination of those. And that central monolithic platform mediates all of the communication between the people who need the data to use for their jobs and the people who generate or have the data and need to make it available. And this monolith creates a massive barrier in between those two important stakeholders. As I mentioned before, data mesh is sort of a concept where we decentralize, where we're decomposing that monolith into many smaller parts. The metaphor here is the decomposition of monolithic software systems into microservices. And just like in the domain-driven transformations of software, we take a domain-driven approach with the data mesh, where we define domains that are sort of aligned along value streams, and those domains own data products. And those data products are these little hexagonal things, which I will explain momentarily. But the data mesh supports the data product development using a common use case agnostic data infrastructure as a platform, self-service infrastructure, and delivery infrastructure, and enforces the interchange of this data through global governance and open standards to ensure interoperability. And so probably most of you are familiar with the concept of fair data. We like to talk about something similar. We have these properties of data that are borrowed from the evolutionary architectures concept, where data is discoverable, addressable, self-describing, secure, trustworthy, and interoperable. And in order to get to that point of having these sort of 6 traits of data, we need to encapsulate what we mean by a data product. So what is a data product? Within the data mesh concept, the data mesh is not mediated by a central platform. There's sort of an underlying infrastructure layer that supports our data mesh, but it's not the data platform in the conventional sense. It's not your big business warehouse. It's not your data lake. It's not your Kafka cluster, your Databricks cluster, whatever it might be. It might have some of those things in it. But what we want to build with the data mesh architecture is a network of data products. And a data product is our fundamental unit of the data mesh architecture. It's the architectural quantum. And the data product is consisting of sort of is defined in terms of its interfaces with the outside world. So a data product has input ports, which we call polyglot input ports, meaning that it can take in data of many different types, many different formats, many different access models. It has polyglot output ports, meaning it's emitting data back into the data mesh in one or more ways, such as through an API, by writing it to a database, pushing it to a data warehouse or a data lake. And then it has control ports, which are used to govern the data product. So this is where we interface our data product with our data catalogs, our lineage tooling, our access and identity management. And what I'll be talking about here is our SLOs and our observability stack. I'll get more into what these ports are a little bit later on. You'll see why this is important. But what we want to do is define these data products through how we interact with them. And then in the middle, these little three little rectangles, that is our processing, that's our pipelining. And so what we do with the data mesh is we move away from the sort of monolithic pipelining within the platform. And we have these smaller pipelines that are owned by the product team, and they have an input layer, a processing layer, and an output layer. And whatever those layers are is going to depend very much on your data product. In particular, it's the output ports that I want to talk about most today, because fundamentally, what I'll be talking about with SLO theory is thinking in terms of the consumer. This whole talk is going to be about consumer-driven data architectures. And so in a data mesh, in a data platform, we're often talking about ingest and data sources and all of these things, and the consumer is sort of delegated as an afterthought. What we want to do is we want to turn this upside down and say, okay, let's lead with the consumer needs. Service level theory, or SLAs, SLOs, and SLIs, are something that we're familiar with if we talk about cloud architectures or any sort of data services. They're going to say, here's our SLA. We're going to give you, 3 nines or 4 nines of uptime. We're going to, do these things. And a lot of people get these concepts mixed up. And so let me briefly introduce them. Service level indicators are measurements. They're sort of metrics that are what we are measuring. So this could be our uptime, it could be our latency, it could be our freshness, right? These are things that should be quantifiable and monitorable. And SLIs are sort of the smallest unit. SLIs inform our SLOs. SLOs are service level objectives. Service level objectives are very, very, very powerful. They're the most important part of reliability theory because SLOs do two things. One, they communicate what the intention of a data product is, or a software service, or whatever it is. It tells the user what they can expect, and it tells the engineering team what they need to do to get there. SLOs should be framed around the value of a product, whether that's a software product or a data product. The more uh, the tighter your SLOs are, the more money you have to invest in the engineering to meet them. And so at some point, there's a break-even point. Does it make sense to push to 4 nines or 5 nines of uptime? Does it make sense to push to 100% completeness in our data? Depends very much on your use case and what the trade-offs are for it. And I'll talk through a little bit of those in a moment. And then SLAs are the things that we talk about. And where people usually get confused is they talk about SLAs as if they are SLOs or SLOs as if they are SLAs. Service level agreements are contracts. They are agreements between parties, either internal teams or companies, such as a cloud provider and its customers. These specify intended service levels, but they do more. They talk about how it's going to be measured and what the expectations of both parties are. So if we miss providing an uptime here, we will provide you a credit based on your billing cycle, et cetera, et cetera. Or if we have an internal SLA, we could put expectations around the timing for a ticket or a bug to be addressed, or the mechanism by which we report um, the issues when we observe them. So we want to think in terms of SLOs because SLOs are the things that are going to communicate our product intention, and it's going to be the things that we use to steer our engineering effort. So that was 10 minutes of introduction, and I apologize for that. But the value of reliability is something that I think that we don't impress enough upon the data engineering community. And the reason that I say that is because when I go to clients and when I talk to other data engineers, people who are in the community, people who are applying for jobs, people who are, looking to ThoughtWorks for help, or even just in conversations online casually, I see the same types of patterns, and usually these are warning signs of something breaking. Many of these might sound familiar. Data engineers are spending all of their time solving ad hoc requests, or responding to analysts. Can you pull me the data? For this and that, and of course, there's a lack of expectation of or lack of understanding of what data actually exists. Or we're running backfills or fixing bugs or dealing with schema collisions and all sorts of things, putting out fires. Or if we go into the data science context, we see months of machine learning development, but no productization of the model. We're running studies. We're saying, okay, we got to do A/B testing, but we're not actually using any rigor to interpret the results, right? These are all common symptoms of an organization that doesn't really get the most value out of its data. And the bottom one here is the one that I see that is the most damaging. When consumer teams are blocked by data processes and data engineering and platform issues, then what happens is shadow data IT starts to proliferate. And then an organization loses control and visibility over the data that's being used, the quality of the data, and what decisions it's driving. This also exposes organizations to regulatory risk, to data breach risk, to all sorts of risks. And this is unfortunately quite a common thing. So what we want to do is we want to, instead of thinking around holding data and obtaining data, what we want to think about is making our data more reliable so that we can get value out of it. And a great reason to do this is because data engineering jobs, as you all probably know, are accelerating. There's a report in the United States that says that data engineering jobs are the fastest growing year over year. They're 50% 2019 to 2020, probably about the same in 2020 to 2021. And this is increasing, and interestingly, the data science job market is contracting. What this is saying is you really want to keep your data engineers happy, so you want to avoid some of those sort of disaster patterns because the market is very aggressive for data engineers at the moment. But also, we see that the OKRs or the KPIs, or however you want to talk about measuring team effectiveness for data teams, are misaligned with product teams, right? And there's this great quote: developers and IT ops professionals had separate and often competing objectives, separate department leadership, separate key performance indicators by which they were judged, and often worked on separate floors or even in separate buildings. The result was siloed teams concerned only with their own fiefdoms, long hours, botched releases, and unhappy customers. If this sounds familiar in the data engineering context, it should, because this is a situation that we're living. But this quote is actually from Atlassian's History of DevOps, and they were describing the pre-2008 world of software engineering, when developers and operations people were often in separate parts of the organization, and software releases for web systems usually were often going badly. And so this is where the concept of DevOps was born, and this concept transformed the way that software is written. If you remember the way that the web was back in 2008, it was highly unreliable. Now things are not perfect, but they're better. And part of the reason that they're better is because we've adopted these ways of working. What this means is that data is a product, and we want to treat it like one. This is one of the fundamental principles of the data mesh concept, is that data itself is a product. So when we talk about data products, we're not actually talking about anything different than the data. What we are talking about is giving data the care and love it deserves, to treat it as something that is a product in its own right, and not just a byproduct of software systems that we are building. So, with all of that said, let's get into some practical SLOs for data engineering. So I've talked about why SLOs are important, why reliability is important, but how do we actually create an SLO for data engineering? In the distributed systems world, we kind of understand now what SLOs are and which ones we should be using. And there's really only a couple different ones that we use frequently. We like to talk about latency, right? Our systems should be fast, right? I shouldn't have to wait 10 seconds for Google to load a Google document or a search result. I shouldn't, I should expect systems to work, right? When GitHub goes down, it's a big deal, and we all kind of like joke about it on Twitter. And when Amazon goes down, AWS goes down, that's a big deal. And we get angry because we're losing a lot of money. But it happens less and less. And why? Because these organizations have created SLOs around system availability, and they treat these SLOs very importantly within their organizations. Consistency, making sure that the information that we're seeing on the screen matches what we're putting in. These are also good SLOs for distributed systems. And these can work for data. They can work for data, but it's often not the most important ones. Availability in the microservices world is something like, you send a ping and the system should respond, and it should respond in under some amount of time, and you have some heartbeat that tells you when that service goes down. That's all great, but it doesn't mean anything for something like a database or a data warehouse. I can ping a database and it will say, yeah, I'm here, I'm awake, I'm responding to queries. But that's not what matters. What matters is the actual data inside of it. A database that is up but has old data is probably not very useful to us if we're trying to do, live analytics. So we have to rethink our notion of availability. We have to rethink the ways that we're looking at data. So how fresh does the data that we use need to be? This is different based on use cases. Are we looking at nightly sales aggregations, or are we looking at quarterly regulatory compliance reporting? Are we looking at real-time marketing? Are we looking at real-time machine learning? The freshness of that data is very important, and sometimes that data is mediated by external processes, right? So we don't, if you have 90 days or 100 days to return an item that you buy in a store, well, um, that sales information can't be, fully correct until 100 days because those customers have that right to return that item. And so you can't, come up with fully accurate information, but maybe you don't need that fully accurate information. If you're trying to do marketing, maybe you can sort of account for the probability of return for that item, right? So there's all sorts of different, often conflicting or competing ideas of what we should be writing our SLOs around. It's very complex. So for data, writing good SLOs is harder. Moreover, a lot of the operations that we do in data are not high volume, high frequency transactions with low value per interaction. For a Google search, Google handles millions or billions or however many searches per day, right? So every search that they do makes, one Google search does not make Google a lot of money. Google makes a lot of money from keeping their system up, right? And servicing a lot of requests. That's obvious. But in data, we don't necessarily have that. Sure, maybe some machine learning applications like a recommendation algorithm, those do have a high frequency, low value per use type of model. But for BI analytics, right, the value per interaction is often quite higher, but the number of interactions is quite lower. Instead of millions of users, we're looking at hundreds of internal users, or maybe even only a dozen internal users. But that report could change the direction of a business. And so we want to sort of encode that value in the ways that we're building those systems. So how can we design a great SLO given that it's complex? Well, let's take this as an example. Let's say that you are an inventory management specialist and you're working for an auto parts supplier. And so you have a network of retail stores, and we live in a just-in-time economy, as we can see from the impacts that COVID has had in our supply chains. But nevertheless, we still have to work with what we've got. So as an inventory management specialist, you want to have yesterday's sales data from all of your stores, and you want that data to be updated by the time you show up to work. And the reason that you want that is so that you can confidently submit stock replenishment orders. And moreover, you want to be the first one to submit those stock replenishment orders because if you get in early, you get better prices from your wholesalers, and that gives you a competitive advantage in the market, right? So we want to compete on data. So if this is our use case, we have a bunch of good questions to ask. When do we need the data by? And during what points of the day are we using it? Are we using it all day long, or does it take me 3 hours to put together the report? Does it take me 5 minutes? How often do we need the data? How accurate does it need to be? Like, do I care if one store accidentally sold an item twice, and is that a big deal or not? So let's start by building an SLO. So let's say that we can answer these questions. We can build the requirements. So if we think about it, the first step is the data manager might say, I want my data to be available every day by 8 a.m. That's when I come in to start work. So I just want the data to be fresh every day. That's my SLO. Is that a good SLO? I would say no. It's a good start for an SLO. It tells us what we're expecting, but it communicates what the expectation is to the consumer, but it doesn't do the other things that an SLO should do. It doesn't tell us how we should engineer our systems better. It doesn't tell us how we can improve. It also doesn't have any notion of a history. This is a binary measure. This is either the data is fresh or it is not. Right? And we haven't answered what some of those detailed questions are, but at least we're starting. The next thing we want to do after we gather the requirements is actually define terms. So what does actually yesterday mean? Is yesterday calendar day? What time zones? Do we have stores around the world? Do we have stores just in Europe or just in North America? How long does it take for those sales reports to be uploaded from each establishment? So what do we define as yesterday? What defines a sold item, right? So Is a sold item a thing that was actually charged at point of sale, or is a sold item something that was purchased online? How do we do that? And what data do we actually need to fulfill our replenishment order? So we could come up with an SLO that has a little bit more context, such as yesterday's transaction data for all stores, meaning the the yesterday ends when the westernmost store closes closes its doors. Must be aggregated, and it must be aggregated by SKU and by distribution center by 8 a.m. every day. So maybe not each individual store, but the warehouse that they get their information from or their items from must be aggregated by 8 a.m. every day. So that's a little bit better. It tells us what we need. It tells us what data we need. It gives us definitions of those terms, but it doesn't tell us how to measure it, right? So how do we actually know if all of our data are present, and what defines if data is up to date? So the next thing we need to do is we actually need to define those SLIs, right? Remember that SLOs are built around SLIs. So let's talk about actually defining those. So what we want to do is we want to think about how are we going to measure if the data has been uploaded. Okay, well, we can create a pipeline that will check through a list of, or we can create a pipeline task that looks through a list of stores and checks to see that our database has every store in yesterday's data, right? So we could do some sort of simple query, show me all of the store IDs and all of the sales, and every store should have a sale um, within within yesterday's time zone or time frame. And once we see that, okay, then we can kick off our job, right? And we'll have this pipeline, right? And we want to send a signal that the pipeline has successfully run and has created the aggregation, and that aggregation is now living in our output port, whatever that output port might be. So we're going to send some sort of indicator. So we could still say our SLO is that we will have a signal that all of the correct data is aggregated, and that signal must be triggered before 8 a.m. every day. And that's a little bit better. But it's still a binary measure. It still tells us either we have succeeded or we have failed. And so now let's think about doing a little bit better. Let's turn that measure into a service level objective. Let's set a target. So one of the questions that we need to ask around this are, how do we know if we've missed a reliability target? How do we accommodate our engineering practices to get better and better over time so that we have incremental improvement? Moreover, how do we avoid reacting to this as an impulse, right? If we miss, let's say the report doesn't finish until 8:15 in the morning one day, how do we avoid turning that into a crisis? Every time that happens. So what we want to do is we want to create an SLO that has some sort of notion of an error budget, some sort of notion of history. And so one way to do it would be to say the aggregation data should not be stale with 99.5% reliability. And stale data is data that has not been updated by 8 a.m. And what we're going to do is with that 99.5% is going to be the amount of time that the data is not fresh past 8 a.m. on every workday. And then we're going to aggregate that over a 20 workday rolling window. So what does that look like in practice? So 20 workdays, so 5 days a week. Let's say that the working day is 12 hours, right? Some people come in at 8 in the morning, some people come in a little bit later, or maybe we have analysts across a bunch of different time zones. So our workday is 12 hours. So there's effectively 240 working hours within our window that is relevant. And we want to make sure that within those 240 hours, 99.5% of that time, the data is going to be fresh. What does that mean? So if we give ourselves a 0.05% error budget, that means that we have over 4 working weeks, 72 minutes of error budget, where if the data is not fresh, okay, that's fine. What does this tell us? What does this give us in a practical sense? So this tells us that we have a little bit over an hour per rolling 4 weeks to make sure that our data is fresh. So if one day the data is not up to date, misses it by 15 minutes. Okay, well, that's really only taking away part of our error budget. Probably not that big of a deal. We can send a message, say, sorry, our data is not available, but it'll be it was 15 minutes late into work today. No big deal. If we do miss the SLO, if we run over that 72 minutes, we know how much. Did we run over it by 10 hours? Did we run over it by 20 minutes, right? Those are two different scenarios that require two different types of interventions. Moreover, if we know that we have a 72-minute error budget and our pipeline takes 90 minutes to run, this might tell us, you know what? Let's put our engineering energy into making our pipeline more efficient. Maybe we can decompose it. Maybe we can restructure our code or the orders in which we run the jobs so that the pipeline can run faster. Maybe we shift left with our data quality testing so that we don't have to rerun the pipelines. If all of our data, isn't there, we can sort of ingest our dimension tables um, in parallel, and we can wait. We can do some better things to make that job more efficient. All sorts of things that we can do to improve the engineering. Or we might say, you know what? We can't do it with this technology. 72 minutes per 4 weeks is not enough. The best we could do is 3 hours every 4 weeks. And then we need to have a conversation about, well, maybe we need better technology, or maybe we need to upscale our cluster, or maybe the challenge isn't on us as a data team. Maybe the challenge is in our upstream data sources, not uploading their data quickly enough, or not, or having issues. And so then we put the engineering focus on the upstream teams. The way that we want to do this, and the reason that this comes into play with data mesh, is that those SLOs touch the data product concept in two places. One, in terms of our output ports. I mentioned earlier that output ports are polyglot. They have different shapes and formats. Here, an output port could be an API. You could be providing data over, say, a GraphQL API or a REST API. Or you could be emitting this data to a bucket, like a data lake or a bucket that you manage. Or you could be writing this data into a materialized table in a data warehouse, right? You could be pushing it to a Kafka stream, publishing it as a topic, or something else. Different use cases will require different SLOs. So in the analytics use case, they just say, it's fine, 8 in the morning, just give it to me. I just want it to be there. And so maybe that for that output port, all I need to do is to create my report and write it as a materialized table or materialized view in a data warehouse. But maybe there's somebody else that also needs that data. And they say, I don't care about the accuracy, just give it to me in real time. Because I want to do, real-time customer marketing or something. So you might start thinking about, well, now I have two different output ports, and now I have two different SLOs for the same data, the same underlying data. So now I have to build two different architectures to serve it. And so maybe my input ports become a little bit different, or my processing layer becomes different, or my output layer becomes different. The output ports in a data product are defined by the SLOs. They are defined by the intention of the data that you're trying to serve and to whom. So when we talk about building output ports, what we want to talk about is what is the service level we are intending to offer with that output port. We don't intend to offer real-time data stored in a S3 bucket. We might intend to offer daily data stored in an S3 bucket. For real-time data, you have to use your stream. This then takes away the question of what's the right architecture, right? So it's not about, should I do a Lambda architecture? Should I do a Kappa architecture? It's, when should I build a Lambda architecture? When should I build a Kappa architecture? And how can I do that effectively and efficiently so that I can support the data product development, so that I can support the users of the data? The second place that SLOs come into play is within our control ports. So the control ports should be used to monitor SLOs and of course, the SLAs through the governance sort of plane within the data mesh. Fundamentally, data governance is nothing but an implementation of very specific SLOs, such as making sure that data is governed, making sure that access is controlled, making sure that certain business glossary terms are implemented correctly. So we want to actually create SLOs in the data product around the governance plane, and we should be hooking up technology to automate the compliance, the monitoring of those SLOs and the compliance with those SLOs, so that we can steer and direct engineering resources into these teams to make sure that they're being met. So how do we do this in practice? Let's get into some of the tech. I've talked about like the theory a little bit, but let's talk about the tech. I mentioned earlier that data pipelines become encoded within your data products. So rather than thinking of having some centralized data pipelining or ETL team, we actually want to push this responsibility into product teams. Data pipelines are just specialized CI/CD pipelines, right? So we know how to do CI/CD for software. We know how to do data pipelines, but fundamentally they're no different. Data pipelines take a bunch of source information, apply some transformations, and emit some sort of artifact at the end. That artifact could be a transformed data set, it could be a machine learning model, it could be a BI report or a dashboard. CI/CD takes in code and data and configuration, builds some software, runs some like compiler maybe, and emits it to some sort of deployment, emits some sort of Docker image maybe, and then deploys it on some infrastructure. These are philosophically the same concept. So why do we have so many things missing in data pipelines that we have in CI/CD pipelines? By which I mean things like testing and validation in pipelines, alerting for when things go wrong. Why do we not have practices like trunk-based development for our data pipelines that allow us to move fast? What we want to do is we want to shift left with our governance. We want to shift left with our quality management. We want to push things less away from, farther away from the consumer and more towards the source. We want to change the ownership of data. And SLO adherence actually starts in your data pipelines. If you can catch errors early, you're going to be much more able to react to them early and to maintain your reliability targets. So in order to do that, we need to rethink how we're doing data pipelines. So there's a couple of different ways that we can do that. First of all, let's move data pipelines into a declarative state. Let's stop writing ad hoc code that is never tested, never see data pipeline code tested. Or worse, we have drag and drop tools. Let's get away from that. Let's use declarative data pipelines, just like we're doing declarative formats for CI/CD or for deployment of microservices, right? So that's one thing that we can do. We can write a little framework that interprets, say, some sort of configuration format like YAML, turns it into an Airflow pipeline or an NiFi pipeline or whatever your tool of choice is, and then we can test that code. We want to put testing both in the data pipelines, meaning data quality testing, but also to test how the pipelines themselves are constructed and the transformation logic. So we have multiple layers of testing. In our data pipelines, we should be integrating multiple forms of data quality testing, including sampling and synthetic data that we can run in a sandbox environment. In order to test those pipelines, that needs to be elevated into what we're doing. And then we need to standardize around quality metrics. We should be doing this, driving this from the top. The governance function should be telling us what our quality standards are and when they should apply. I have just a few minutes left, but I'm wrapping up. YAML, I know some people hate it. I love it. I apologize for that. Actually, I make no apologies for that. It's totally possible to take YAML configuration and to use this to build your data pipelines. I've done this with clients. It completely changed the game in terms of the reliability of our systems. Moreover, we were able to integrate SLOs as code into our data pipeline definitions. So everything that we needed from monitoring to data quality testing to data transformation logic to even what fields we should be ingesting from what tables, all of that was in a declarative format. It was inspectable, it was auditable. We could tell where the PII lived. We could tell all of that stuff in a very simple, human readable format that was version controlled. This is so important. I can't stress it enough. And then observability, when I ask people, oh, are you observing your data pipelines? They say, yeah, I've got Spark logs. That's not enough. Observability is not just about how our performance is doing, but it should tell us how we can improve our performance moving forward. It should give us clues as to where we can improve. Can we look at making our jobs more efficient? Can we look at making our data more accurate? This is the most important lever that we have to affect what our engineering teams are doing. And so the image I have here is the way that we were using Redshift. We had high CPU, high disk utilization. Our observability told us that. We made sure to hook up monitoring, and we investigated how we can change the way that we're using Redshift, and then the effects were dramatic. So the cost savings and the efficiency gains that we were able to get just through this observability lens was immense. The problem is that the dashboarding and monitoring tools that we have are not really that good for data SLOs. We have really great tools for monitoring distributed systems SLOs like latency and uptime. They don't work very well when we have to have bespoke SLOs like completeness or accuracy or data volume or data anomalies, right? The types of SLOs that we would expect for data. We have to still write a lot of tooling on top of that. But that's a great opportunity for innovation. The data mesh is a connection between data products output ports and other data products input ports. To make this actually work, you want to create contract testing between teams. You want to create contract tests for your data as you do for your software. This will prevent a lot of those issues that I described earlier, like somebody changing a schema in some upstream ERP system and that affecting your analytics downstream and causing a week worth of delay and stress. If you can bring these concepts together and build contract testing and other SLO adherence tools, then you can avoid those types of issues. However, there's no good frameworks that I've found. If you know of one, please let me know, for actually doing this within the specifics sort of context of data. So if one of you wants to write one and it's good, I will be happy to promote it. So I am just about on time here, and I have one more slide to talk about before wrapping up. I mentioned earlier that we want to build consumer-driven architectures. What I'm really talking about is the death of the monolithic central platform. Time and time again, I see people starting from data sources and moving left to right. They do ETLs, they do transforms, they do these things, and then they get it to the analytics team, and that data is not what they want. And so then the analytics team says, no, this is not what I need. And then that request has to go all the way back through the chain to the source through multiple rounds of prioritization. This round trip feedback cycle often takes 3 months or more. Decentralizing is a process of turning this upside down, starting with the consumer's need and building the architectures that they need to support their use cases. Shorten the feedback cycles, right? And you might still have to go all the way to the source, but at every step you should be having a tighter loop so that you're building the right thing. This long back and forth costs us time and money. But more than that, reliability is always in the eye of the beholder. It's not something that you can define. I see people say building products all the time. They build a product and they say, what is the SLO now? No, you have to start with the SLO because you have to start with the user, because reliability is what matters to them, right? It's not something that you can define after the fact, and it's not something that you can define without the user's perspective. In order to do that, we can't have, because you have so many different users, you can't have a single perspective on reliability for any of these monolithic architectures, because every single one of these consumer teams, these little pink and purple hexagons and triangles, every one of those teams is going to have a different opinion on what reliability means. So in order to service all of their needs, we need to decentralize. We need to decompose the monolith. That's all I have. Thank you very much. And if we have time for questions, I'll be happy to take them. Otherwise, you can reach me on Slack or Twitter. Thank you.
Perfect. Thank you, Emily. If there are any questions, you can write Emily directly on the Pine platform or any way else. thank you very much for the interesting talk. Super interesting, and I'm going to have an awesome conversation with my CTO tomorrow about this because it's a concept you should follow up on. Emily, thank you very much for the talk. Again, super interesting to listen to, and looking forward to seeing you next time.
Great. Thank you. Ciao.
Perfect.